Oh,
All right, guys. Thanks for coming out. I appreciate it. We're trying to build this, and so it really takes the effort of each of you, coming out, telling, spreading the word, getting your friends and coworkers out. I really appreciate it. We have a site right now. I'm not going to do a slide on this. The information can be found on meetups, but we have a site, pdxvidtech.com, where we kind of host the after. Nicholas here is doing the video capture tonight, so we'll have that video, and we'll have any pictures and other information on that site. And then pdxvidtech@gmail is the email to contact us if you have any questions, or the meetup site. My name is Dan Sparaccio. For you that don't know me, I work at CBS Interactive, based here in Portland, but my main office is in San Francisco. I've been doing streaming stuff for 15 years. I enjoy the industry, but this is about more than just streaming. So if you have talks that you want to do that are not streaming specific or not in anything to do with the web that are video related, we're pleased to have those as well. So we want to broaden the scope, try to get as many people in as we can. So again, thank you for coming out. Enjoy it, and we'll start with Al, and I will invite you up to do your talk. Thank you.
Okay. Well, thanks guys for organizing.
I don't want a beer thing in front of you.
Okay, today I'm going to talk about models of visual perception. In the literature, you'll see human visual systems, so you'll see HVS more often. Just for the title of the talk, I thought perception would be a little bit more explanatory. Okay, I purposely made this low contrast. Can you guys read all the text on here? All right, so it's definitely above your detection threshold. So sensitivity is considered the inverse of detection. So if we lower the contrast until you can barely see it, then we say, all right, these intensity combinations next to each other is very apparent, right? It could be based on the pattern. But we'll see more of that. All right, so this is a real slide. Okay, before I get started, I wanted to, how many of you have worked with, say, the contrast sensitivity function? Okay, so I was hoping it wouldn't be like everyone's like, yeah, we're color science experts. I'll be like, all right, at least my time for these slides. So I've had some experience with working with human visual models, human visual system models, mostly at Dolby Labs, worked on a variety of things that are related. A little bit also at Kodak. I worked with Scott Daly at Dolby. Actually, I met him at Kodak. He's like, well known for developing models for human eyes, so it's great to learn from him. I had a great mentor at Kodak, Dr. Shenchi Lee. He also a color science expert, and other stuff in case anyone wants to talk about that geeky stuff after the talk. Okay, so what is a model of human visual perception? These are my definitions. You might find different ones if you Google for them. It's a quantitative model used to describe some property, some aspect of human visual perception. It could be your color sensitivity, your sensitivity to contrast. How high a frame rate do you need before you'll say, all right, that motion looks smooth? Things like that, right? Various aspects. The human visual system is very complex. And usually a model will describe that using an algorithm that will end, right? It's just a series of finite steps, or an equation, or a set of equations. Now, perception, sort of by definition, is a subjective experience. So these models try to quantify that, right? Like randomness it's random, but stochastic processes makes it a rigorous science. So here, even though perception is subjective, there's a certain commonality among people. There's a certain statistical spread, and if you can quantify that, then you've got something that you can turn the crank and come up with. Maybe surprising results that predict something, and then it matches data in the field, and you go, wow, I found something. So even though we have something subjective, there's a certain biological commonality in human visual systems, the way our brains process imagery. And so I'd say a model tries to map something that you can measure directly, right? These are things you can measure with lab equipment. What's the frequency in time? What's the frequency as you scan across picture, like spatial frequencies, and map that to something that you quantify as the perceptual properties of a standard observer. Can they detect something, or do they say these two things look very different and these other two things look very similar? Okay, and oftentimes what people judge, you convert it to some sort of number. You may be familiar with sort of the forced A/B testing, where there's a forced choice. So if people aren't sure, like, well, it could be this, could be that, you force them to choose, but if you do it often enough, then you can see if they're really guessing. If they're not sure, then they'll be about 50%, one way or the other, if you have a ground truth. But once you get 80, 90, 100% one way, then you know, okay, they're really seeing something. So I'm talking very abstractly now, but I'll show something a little bit more concrete. So I'll move into some examples. So how many of you have heard of Weber's law? Okay. This is something that, what was this, the E.B. Weber? I forget his first initials. But he initially discovered, he noticed this in weightlifting. So here's a very simple example. Suppose someone takes a quarter and they coat it with felt and they put it in your hand. Why felt? So they can put something on it and you won't hear it. So they close your eyes, all right, close your eyes, and then they put 2 quarters on top. Will you feel the difference? I feel it. It's pretty different. Now suppose you're loading up a leg press machine with 45-pound plates, and someone says, well, wait, hold that plate, and you're like, why? Close your eyes. Now I'm going to put 2 quarters on top, coated with felt. Do you feel it? Like, I don't know, it's 45 pounds, right? So it's proportional to what your sensation level is at, how much change you need to feel it. That's what Weber observed. And he thought, hey, does this apply to all the other human senses? And I think he found a certain truth, like true as in within certain ranges of sensation, that this logarithmic law applies, right? When the amount of change you need to feel a difference at a certain given level, you can quantify that as a delta I over I, delta something over that something, right? And so, what expression will solve the differential equation where you say d something equals c times that something, right? And if EQ is the only solution, is an exponential. So this shows, but since we're talking about the sensation side, it's reversed, so we're talking logarithmic. Right, hearing's logarithmic. You double the frequency and you go, well, that's only 1 octave higher. You double it again and double it again. It's 8 times higher, and you're like, no, that's only 3 steps. It's log 2, right? Same, that's with audio pitch. What about audio loudness? Why do we use dB for that? Why do we use log scales on luminance, for on plots. It's because the human visual system, the human audio system, there's a lot of logarithmic transfer functions in our systems because we want to pack in a wider dynamic range, right? If we don't use log, then we're really, really limited. So sunlight versus candlelight, I forget the ratio, it's like 100,000. It's many orders of magnitude. And we achieve that through the pupil dilation, but very powerfully, we've got rods and cones, and when the rods kick in and dark light, there's a chemical change that can take up to half an hour. That's why when you wake up in the middle of the night and someone's like, what's that noise? Let me turn on the light. And you're like, oh my God, I can't see. It's not because your pupils are taking minutes to shut down, right? That happens in seconds. It's because these chemicals take a long time to flush out of your retina so that you're back to regular light room illumination levels. And that's why at night, if you stand outside long enough in the dark, but the moon's out, pretty soon everything's like, hey, I can see all my camping gear. It's because your eyes go through this change. So these are like amazing things that we have, and modeling the human visual system has to take that into account. So this law says that the change in intensity, you'll feel it when it's proportional beyond a certain percentage of the level you're already at. And someone said, well, you got this little knee here, see this plot here, if the first law there, the delta I over I equals C, if that was true, then this is that delta I over I, it'd just be constant. So, but if you add in this threshold here on the bottom, then percentage-wise, it shifts everything down, but it shifts the lower ones down more. So it will flatten this a little bit more. So at least within a certain range, it's an approximate law. Okay, so this is for what's the bare amount of change you need to detect that in luminance. Okay, and here's another example. These are called McAdam ellipses. I don't know if any of you have heard of that. On the CIT chromaticity diagram, if you have a color that you show somebody, and then you can ask the question, how far can I move it before someone will say, ah, I detect a difference. And this is actually done, there's different ways to do this. Temporally, I haven't heard of it. It's usually like simultaneously a static image, right? You'll show a surround and then you'll show a target in the middle. And you look at it. And people tend to like a 2-degree foveal view. So you make the target so it covers 2 degrees worth of angle. I mean, I don't know how that converts to straight. It's like 2 degrees wide this way in one dimension. And because the fovea, the cones are at the highest concentration in that 2-degree view. That's how the CIE 1931 color science was done to even generate this plot to begin with. So anyways, this is kind of interesting that people do these like microscopic measurements. Like they look through a microscope at the retina and they find all this cool information. Right? So these these things come out, and then the McAdams ellipses are supposed to indicate how far you can wander from a color and still think it's the same color. Right? So you can see if your eye is very sensitive to something, there'll be a small ellipse. Okay, so today I'm going to try to. I probably have more slides than I can cover, so I'm going to skip a few. I know Dan want me to fit it in the time slot. So, but I'll at least try to touch on all of these. And this is by no means an exhaustive list. There's tons of other ones. I thrown in a few other ones on a slide that says, for further reading, I guess you can Google those other terms. Okay. So I'm going to talk about spatial frequency, temporal frequency, sort of combining the spatial temporal contrast sensitivity function, how the CIE came up with that funny, what do they call that? That CIE diagram. It's like half a potato chip. The spectral locus is the curve, the boundary on the outside. High dynamic range, how that diagram shows how that affects color spaces. And I talk about some of these because motion is important, and there's been a lot of work done on that. There just isn't time to fit in math models for those, because that gets pretty time. Okay, have you seen this? Okay, so as you get closer to the screen, it's hard to do here, but like you find one of these on the internet, look at it on your monitor, and keep stepping back from it, and you'll see the gray kind of creeps down as you get further away, because your eye, the retinal cells start blending in the black and white finely spaced lines, right? Because if you're super far away from, let's say, 2 people, one's wearing a green shirt, one's wearing a red shirt, you go far enough away, they're going to look like one brown dot, right?
So at the top, it looks totally gray to me. Is this vertically?
Yeah. Okay.
symmetric?
Sorry, I didn't explain it. Yeah. Good question. So as you can tell, the wave's way faster and faster as you go this way. So the frequency is this axis, and as you go up, the contrast kind of disappears. It goes into gray so that the whites and blacks come close together. So just looking at this, you can see that your eye is probably most sensitive. Maybe somewhere in here, like DC values, the sensitivity is supposed to be pretty close to 0. It peaks probably around, later on I can show you the plot, something like 15 cycles per degree, maybe it's 10 to 15, and then it'll sort of taper off. I mean, we're not at the right spacing, but if you get it to be like every other pixel, and you're far enough away, then you'll see that you'll start seeing just gray up at the top, but you can see some sort of shape, right? Sorry, this isn't the best display system, isn't the best image to begin with, but I'm hoping it gives you an idea of how your eye's response to patterns like this, and to give you an idea that this is one of the ways to test for contrast sensitivity. Okay, so when you test people, you can do this forced choice A/B, or however you want to do it, but you can find where do they start trailing off, where do they think they can't tell, like, might be gray, might be a pattern there, let me just guess, right? Then that's where you can say, for that person, there is a detectability threshold that you're crossing from being able to reliably say, yes, it's there or not, to not being reliable. And luminance, you're more sensitive to luminance for change further out. So higher frequencies, luminance, which is brightness, trails off later as you have to get to higher frequencies, whereas your cones that detect color, they'll trail off a lot faster. So these are like aggregate data. They try to find young, healthy people with normal vision. They're not colorblind. They're not like extreme, they don't have a viewing disability. And then, and some researchers are just like, well, I'm going to do it because I'm doing the research, and then I'll get my buddy to take this test, right? So sometimes you'll see a paper with like 2 people, maybe 3. So, it's kind of like the psychology papers I used to occasionally read, and they can't reproduce the results because the sample size is too small, right? You get another group of people who have different characteristics. So, but over time, if you look at these plots from lots of different researchers, there is a general pattern like this. And that is why 420 coding works, right? You don't have to show color with the same spatial frequency. You don't really notice the difference because you're there where your eye can't tell the difference anyway. So you might as well throw that info away. That's why you can low pass filter color if you want, or just subsample. Okay, so Scott Daly, he developed a CSF, and his testing methodology was really thorough. Like you should see some of his papers. He has all sorts of these. He doesn't just do one thing. He'll try like all these other things, and he'll tell you why he decided to pick this one thing. So this is a static contrast sensitivity function. So what you saw was a static image. This one, he did that, except he did two dimensions, x and y. So we only saw variation like this way, right? But he also had patterns that went that way simultaneously. He could also do the same thing and just rotate it, but he did all sorts of different tests. Anyways, this is the contrast sensitivity function he came up with. So sensitivity is really 1 over the threshold. But anyways, as you can see, kind of the 45-degree angle has kind of a lower sensitivity along that direction. These are cycles per degree. That's that's a standard when you want to measure like visual things to do with spatial frequency. How many sinusoidal waves do you get in 1 degree of view? And the human eye can, if you have 20/20 vision, you can tell the difference between a black and white dot if it's 1/60th of a degree. If each of those dots takes up 1/60th of a degree under what they call photopic view conditions, where your color vision goes bright enough for your color cells to be active, as opposed to like moonlight, where it would just be your black and white cells active. Okay, this is a figure for different viewing distances. Even if it's sometimes the same cycles per degree, somehow when you focus near and far, that'll vary your CSF. And so he said for that, you would have to do, you could just take the envelope, right? There are convex all around all the different CSF plots. And then that would be considered a CSF for that range of viewing distances. Okay, so this is the thing that leads to 60 pixels per degree of view. So this is a standard like eye chart, letter E, right? And so 20/20 vision is you have to view this letter of a particular physical size at a particular like absolute distance. And if you can see this E, where it's got, I guess it's got 5 dots, right? Like if you look at just how much variation as you go up, it's got 1, 2, 3, yeah, 5, and that covers whatever the math works out to be. There's each dot is 1/60th of a degree. So it's under pretty bright viewing conditions, right? I mean, when you take this eye chart, they don't shine this like really wimpy light. It's decently bright. Okay. So here's an example of how you would use that cycles per degree limit to determine how far you need to sit from a UHD TV set to make sure you're getting all the detail that's displayed, right? Because if you sit, I don't know, here to there, and you look at a cell phone, it doesn't matter if it's quad HD or 8K or whatever, right? You're going to be like, it might as well be 320p, might as well be 160p. So there's some viewing distance where you want to be so you can see every pixel but not see giant squares, right? So, so you can just do the math and say, all right, suppose I've got a really sharp contrast screen and I have 20/20 vision. How far back? And I want to see more detail and get closer and closer. Where's the point where I can stop and say, all right, I can enjoy it? So if you go through the math, it turns out for UHD, it's about 3/4 of the diagonal size. So 55-inch screen, you got to sit closer than 55 inches, right? About 42.5 inches. For 1080p, then of course it's like 1.5 the diagonal size. And this is kind of conservative. This is assuming you have really good vision and can see all that detail, right? I mean, encoding can kind of mess that up. And there may not be patterns that need you to distinguish between each neighboring pixel, each pixel and its neighbor, right? So if you look at manufacturers, for some reason they like to use lower CPD values. I'm not sure if that's a marketing thing where if you sit further away, you'll go, oh, it's super sharp, you like your TV more, or if they just figured most content doesn't really push you to that limit of black pixel and white pixel. I mean, this is like fully on-off. So, that's not a natural pattern that you typically see. But anyways, just so that if you want to compare this result with stuff you'll find on the internet, you might find that they're a little bit more lax and sit further back. See, if you don't sit close enough, then you're going to be like that girl. All right, so some benefits. You can use CSF to predict how noticeable something is, which is nice for lossy compression, right? Like, how do you tell if something works in terms of throwing away the right info so that people don't really notice? Then if you have a rigorous model that you've developed carefully, applies to most people, then you can have confidence to know, I threw this away, it's not going to be visible. You don't have to constantly do your own test over and over, your viewing test. I mean, it's good to do them anyway, but this kind of gets you close for a lot less effort than if you ran your own test and tuned your compression algorithm sort of from scratch. Okay, a visual quality metric, right? So you can, if you want to do bit rate versus quality, the sort of rate distortion curve, the trade-off along that, you can have a subjective metric that is automated and is well quantified. Okay. So, can anyone think of any other benefits, ways to apply the CSF? Just throw that out there.
I think I could save money by not buying a 4K TV.
Yeah, it depends on how far your couch is from.
Yeah.
That's right. But there's other reasons why 4K may not help. It depends on the camera. Sometimes they use the lenses that were great for 1080p, and they're just not sharp enough to resolve, right? Just like sniper rifle lenses have special fluoride coatings and stuff like that. They may not have done that with camera lenses. Right? Depends on how old the technology was. Okay. Watson did lots of early work in the 80s. He's continued to do it. I think the one where he talks about the spatial temporal CSF had something like 2,000 references to it. So I guess someone's done good work when that happens, right? So what he did was he took sinusoidal gratings, like the one you saw, and he let it fade in time. So you go from the grating, which still had the increasing frequency and the fading away, but then you would fade the whole thing to pure gray, and then you'd fade it to the negative image. So then it could sort of swing back and forth between the regular image through gray to its negative. And then the faster you flicker it, the better response you'll get up to a certain point, and then if you flicker it too fast, then the whole thing just blurs and you can't see anything, right? Because you flicker, or you swing something back and forth fast enough, eventually your eye will just, through retinal persistence, will average it out. And so he did this sort of simultaneously in both domains, which is really nice, because then you can take this model and you can say, all right, if I've got fast motion, how much detail do I need to keep? And Scott Daly also confirmed this in his own different tests, that if you have high frequency components in an area and it's moving fast, you can quantize the living daylights out of it. You really don't have to code it very, very much. And so this is like perception-aware video encoding. He proposed this in the early 90s. And so a lot of people talked about his work. Researchers will read it and go, okay, well, let's apply it and take it further, and we'll publish other uses of it or refinements of his model. And Watson was also in the same category. He did this work early on. So this is some good work. You notice trollins there. It's a unit that's normalized to like a square millimeter of the pupil's opening. That's yet another partly subjective. It's a measure that takes into account the human eye, right? It isn't just like joules per square meter, whatever, right? Like that you could measure. This is like it's gone through the pupil. Okay, so I'm going to move from frequency in space and time to color. So totally changing gears here. Sorry, I'm kind of going too fast probably because I have too many slides. I should pause for any questions so far. Okay. Okay, these are, I'm going to talk about how the CIA, I think it stands, it's like a French term, I can't pronounce it, I'm going to say the English equivalent was the International Commission on Color. Anyways, it was a big effort in 1931 to come up with a standard observer when it comes to color perception. And that's where they got that CIE spectral locus. But I'm going to start out with just like some very low level measurements that you can measure in a lab. This doesn't involve people running experiments and writing down anything. You can measure the photoelectric response of different retinal cells. Right? So SML is short, medium, long. You can kind of think of it as blue, green, red. So these are the responses. They've been normalized so that they have the same peak. Blue actually is like very low. If you look at the NTSC matrix, right, the blue component is like 0.17 or something, or 0.2. It's somewhere in that range. So here, this is just so you can see it. And you'll notice that green and red are very close together. It seems very suboptimal, right? Your green and red receptors are not orthogonal, and they should. I wish they were. In the CIE, the display technology could be a lot simpler to at least to do the math. Okay. This is to show this is the sort of a black and white response. It still obviously has limits, fall-offs and the frequency it can detect. But this is just to give you sort of a comparison with the color detection. So you'll see that your green receptor response is the closest to the limits. In fact, that was one thing they used. They say when you transform things to get that curve to fit, like all in the positive quadrant, they wanted the luminance, the sort of greenish basis function to line up with the luminance sensitivity. Okay, so this is a tetrachromat. There's fishes, there's insects, there's birds that have 4 color receptors in their eyes. And one study suggested that between 2 and 3% of human women are also tetrachromats. And I have a guy friend who is, so he's very rare. I think it's because the X chromosome contains more of the cone, I think they contain the cone pigment producing, the photoreactive pigment producing gene. And so, men have one shot at getting that. And women get two tries at it. And so somehow mutations for tetrachromats happen more often than females. And so 2 to 3% of the population potentially, if that one study is right. And anyways, my guy friend, his name's Curtis, and he can see things with 4 color receptors, and he'll be like, "You're that blue, and your shirt and your pants, they don't match at all." And I'm like, "They look fine to me." And everyone else around is like, "They're blue." He's seeing it in sort of a 4-dimensional space. Well, these birds probably have this because, I don't know, they must look at vegetation and must need to tell like what's right, or I don't know what they do. I'm not a biologist. But see, as you can see, this is nicely spaced, right? This is much more orthogonal. So if they have a CIA color curve, it wouldn't be this crazy thing that has all sorts of redundancy. This is, to me, I don't know anything about this, but just looking at this, I'm thinking there must have been some optimization that was biologically motivated for this biological design to be favored, right? I heard that this green curve came in out of a mutation, so we got lucky. But it did help us survive. One theory, one conjecture, I should say, is that humans needed to be able to distinguish between food and the green leaves. So you could find the fruit easy, or at least find the right fruit. And so therefore distinguishing between green and something kind of close to green was helpful. That was according to one paper. I'll pick that up in case anyone wants to see it. Okay, so, oh gosh, timelines. All right, so I'll at least try to finish the color stuff. Back in 1931, I wish we could do it again, but everything's so ingrained with the primaries they chose. Rec 2020 uses these color primaries. They don't want to go back and do experiments and then have to convince the entire industry to throw out everything they have and replace it with some new color primary-based system. They chose this because mercury lamp it was easy to get these numbers, and 700 was far enough away that by the time you got around here, the red response was about something like 1,000 times higher than the green. And so if they were off of it or not, it didn't matter. They weren't contaminating the green response. And so there were a lot of these practical things that made them choose what they chose, and so we're just, the imaging systems are kind of tied to that. So given these primaries, given any spectrum, once you have to take okay, so these are the response curves, right? So these are the basis functions. They take this, a continuous spectrum is like a vector with an infinitely many number of elements, right? And so you can still take the dot product, it's just the integral. So you multiply the spectrum that comes in by, say, blue, pointwise, and then you integrate, right? Or you sum if it's digital. You do the same thing with green, you do the same thing with red, and you get 3 numbers, and you go, that's my RGB value. Okay, but it's really the continuous domain, and this is the projection. You're projecting infinite dimensional signal down to just 3. So, but if you take a specific set of primaries, you may not be able to get the stimulus in your eye, you may not feel it's the same. So they did this color matching experiment. They said, let's take these 3 primaries, let's shine a monochromatic source that could be any frequency, and have people turn these dials to try to match the color. And then when they couldn't match the color, they could go and add red to the other side, to the source monochromatic color, in order to bring it to match. Because the green and blue, the green sits somewhere around here, so you couldn't get out to that monochromatic source. But if you added red, you could push it back, so it would be on that line. So that's how they did it. That's why you get negative. This is not, you didn't subtract red out of, and saw negative red. They actually had to add it to the monochromatic source in order to get their colors to look the same. And something they don't tell you, if you go back and read the original report, I happen to have access to it when I was at Kodak, is that some people gave up. They're just like, I can't match it. They got frustrated, they just left. So, that's not widely publicized. So it makes me wonder, how good a model could we have if we got 100 people to do this instead of the 10 plus, I think, the 17 total people. I mean, they're supposedly people with good vision, but it just makes me wonder, how good could we have made it if we had today's technology? If we could have picked different primaries. I mean, I don't know if quantum dots can be pure. I've heard of tunable lasers, but it's hard to imagine that we couldn't do better these days, right? But that was what they had, and it's held up quite well. Right? NTSC was a great success, PAL, so on. Okay, so after you get these color matching curves that has this negative, what do you do with it? Well, they were using slide rules back then, and they're like, we don't like dealing with negative numbers. And so they're like, well, let's transform this. So they pick these imaginary colors that you can't achieve physically, but they did this as a mathematical mechanism, I guess, or trick, or whatever you want to call it, method. And they placed these so that here it's tangent to the curve. They made this big triangle had to contain all the points in, so that these 3 primaries could be used as basis functions to get to basis vectors to get to any point inside here, right? You just do a linear combination of any of them. They wanted the white point to be 1/3, 1/3, and so on. And then after they transform it, that's where you get this familiar CIE plot. Okay, so that spectrum that went negative, now it stays all positive, and they're happy with their slide rules. And then that actually transforms these into your basis function. And this is what you take the dot product with of the spectrum. It gives you XYZ. They call it XYZ because it was different from RGB. XYZ, you take X and you divide it by the sum of X plus Y plus Z. Do the same with Y, and that's where you end up here. And that means if you have 2 different colors, as long as a person kind of falls into that standard observer model, where it's an approximation for how they perceive things color-wise, then you can take, let's say you got a shirt here and a rock, and they both kind of look reddish. Take their spectrums, mathematically go through this. If their XYZ values are the same, then that means the average person, or the person with good vision, should say, yeah, the rock and the shirt are the same color. So you can use this for industrial design or whatever. You can use it predictively. And this is just definition of saturation. It's how close you are to the spectral locus. So you're not tainted by other monochromatic type or non-monochromatic sources. Okay, and, all right, okay. So I'll stop at perceptual color spaces. So one goal is these color spaces are pretty highly nonlinear. And so on this diagram, the difference over here, as you recall the mean atoms ellipse here is very small. You're very sensitive to changes in blue, but not very much in the greens. And so people are like, this is a pain in the butt. How do we tell if this pair of colors is about as different as that pair of colors? And so there's been a big effort to warp this space into something where you can measure the Euclidean distance between 2 points anywhere, and it should represent perceptually how different you'll feel these two colors are. So HSV is sort of a very rough color space for that, but it's still not there. But CIE LAV space for daylight D50, which is like pretty close to 5,000 Kelvin as the white point in the black body spectrum. It's highly nonlinear. I remember there's a cube group. Yeah, there it is. It's pretty slow. I actually generated this once. This is somebody else's plot. There's like this really weird wispy curve if you do a higher resolution sampling. But anyways, this was their attempt to have a Euclidean distance sort of uniform color space. I think it's called uniform color space. Okay, so you've probably seen this, right? Like all the different things overlaid on the CIE color space. Because these different color spaces have different sizes. The gamuts are wider for some because they use primaries that are further apart, closer to the monochromatic sources. And it's kind of cool that here they choose imaginary ones. It's not like you're going to create one with a light source that you can't produce in reality. This is just sort of a mathematical thing saying if you've got a color, use these primaries to define how far out you can go. And then if you've got an imaging device like a printer that has a lot of different cartridges, have you seen the gamut for some printers if they've got like 6 different colors? It's like a 6-sided, it's like a lopsided hexagon, right? And the more pure they can get those ink colors, the further they can push it out towards the edges. And so if you have a really, really wide gamut, even if it's imaginary, it still mathematically allows you to hit points, that are closer to the edges. And therefore you get a wider gamut, you'll get higher saturation. It'll help in HDR, right? Because as brightness goes up, if your color space is small, it gets pinched, so you don't get any saturation as you get brighter and brighter. So if you can really open that up, then you can have a huge color volume. That's why people talk about 2020 color volume. Okay, so, sorry, I forgot, I got the next slide. So as you go up in dynamic range, your color space also grows. This is taken from Scott Daly's paper. Okay, so maybe I should stop here.
Is it a good point to wrap up?
Yeah, this is, I was going to move on to blur, so I'll just go to conclusion, and I got attributions in case anyone wants to see.
Are you okay with sharing the slide after for?
Yeah, sure.
public? So we'll have that on the site then.
Okay.
If
I'll just
you're okay
generate
with
a
that.
PDF.
Yeah, and if you want to communicate anything out, we can.
Okay.
All right, well, thank you very much, Al. Take a couple minutes to get set up here. There's a bathroom too, right and left, if anybody needs it.